Welcome to today's video on electromagnetic radiation. This is part 1. In today's video, we are going to focus on light behaving as a wave. In part 2, we'll focus on light behaving as a stream of photons. So let's get started with what light behaves as a wave. So waves have two properties. Waves have a wavelength, and they also have a frequency. And the symbols for each are noted right over here. Wavelength is this symbol here, Greek letter lambda, looks kind of like a backwards H. And wavelength is simply how long the wave is from peak to peak. So if I measure from here to here, this distance is wavelength. I could do the same thing down here between these two waves, and I notice that the wavelength is longer in the bottom picture. But wavelength is simply how long the wave is from peak to peak. Typically, our units for wavelength are going to be in meters. Frequency is how many waves pass through a given point per second. So frequency is telling us how many waves. And frequency is with this Greek letter nu. It kind of looks like a V, but it's slightly different. So it's a Greek letter nu. I can look at the top picture, which has the shorter wavelength, and I can count how many waves are kind of in this period of time. So I can count 1, 2, 3, 4 waves. 4 waves per second. The bottom picture only shows me 2 waves. 2 waves per second. And so these relationships here are important. If I have a short wavelength, I can have a high frequency. I can fit more waves through a point in a given period of time. If I have a longer wavelength, I get fewer waves. So that is defined for us, I can see that on the electromagnetic spectrum, specifically in the visible areas of light, how it relates to energy. So long wavelength gets me a small frequency, low energy. Short wavelengths means that I have a high frequency and a high energy. So if I notice here with my colors of light, down here, 700 nanometers is longer than 400 nanometers. So these are my longer wavelengths. So I have smaller frequencies with that. So red light has a longer wavelength. Purple light, on the other hand, this has a short wavelength. And then I'll have a higher frequency. And we'll get to energy more in part 2. Increasing frequency. Okay, so here are my 2 letters again. Wavelength, again, is the Greek letter lambda. Waves will have a frequency too, how often the waves pass. And the thing to remember here is that all radiation travels at the same speed. So I have wavelength times frequency equals c, which is the speed of light, the velocity of light. And this is a constant. The speed of light does not change, and nothing will travel faster than the speed of light. So c equals 3.00 times 10 to the 8th meters per second. Lambda, we said again, was wavelength. Typically that's going to be in meters. And then the Greek letter nu is frequency. And my units for frequency are hertz. Another way to write hertz is seconds to the -1. An even additional way to write hertz is to say 1 over s. That's what the seconds to the -1 means, because it's the number of waves per unit of time. Frequency is not a unit of time. So let's do an example. The wavelength of green light is about 522 nanometers. What is the frequency of this radiation? The first thing that I'm going to do is write down my equation. So I will have C equals lambda times nu. And then I'm going to read the problem to see what I'm given and what maybe I have to look for. Wavelength, it tells me, is 522 nanometers. Notice my unit there is nanometers. I have to put nanometers into meters. I'm going to lock that away. I'll show that in the example here. It's asking for a frequency. What is the frequency. I don't know frequency. So I need to rearrange my top equation to solve for frequency. Frequency I need by itself. I should end up with frequency equals c over wavelength. Let's convert our wavelength here because I noticed that it's in nanometers. So I'll do that off to this side over here. 522 nanometers. If I remember from my prefixes and my powers of 10, so nanometers will go on the bottom, meters will go on the top. In 1 meter, there are 1 billion nanometers. Nanometers will cancel out, and so I end up dividing these two numbers. What I get then is a very small number. I get 5.22 times 10 to the negative 7 meters. That's my wavelength. So I haven't solved my problem yet. All I've done is convert nanometers into meters. You might not need to do this every time, but just pay attention to your units. So now I'm going to put these numbers into my equation. So c, remember, was our speed of light, 3.00 times 10 to the 8th meters per second. And I'm going to divide that by this wavelength, 5.22 times 10 to the negative 7 meters. I should notice that meters will cancel out, leaving me with seconds, but in the denominator. So if I punch these into my calculator, again, when I punch numbers into my calculator, I want to make sure that I am using the EE button or the EXP button to say times 10, all right? If I punch that in, I will get, one second here, I will get 5.74 times 10 to the 14. And I've got 3 sig figs on my answer, and it's in scientific notation. That number should make sense because that's going to be a high number of waves. My wavelength was pretty small. And so now the question is, what units go on my answer? Well, I was looking for frequency, and so I know that the units for frequency are hertz, Hz. I also know from my equation that meters canceled, leaving me with seconds in the denominator. So another way to write that is 1 over s for seconds. You can write either one. I'll write hertz probably more often, but know that they are the same thing. So this is my final answer here. All right, and that was our wavelength, or sorry, that was our frequency of the green light. Let's do another example going the other way. So here I want to also determine the type of radiation. So if I know, sorry, the question says, what is the wavelength of a photon? A photon, remember, is a particle of light that has a frequency of 2.10 times 10 to the 14 hertz. I want to put this answer in nanometers and determine the type of radiation. So let's mark the problem and to see what we need to figure out. I have a frequency this time. I don't know the wavelength. Wavelength is what I'm trying to find. What is the wavelength? So using my equation, C equals lambda times nu, wavelength is what I want to get by itself. So I end up with lambda equals C over frequency. I'll rewrite that down here. Again, I know the speed of light is always 3.00 times 10 to the 8th meters per second. And my frequency, I'm just going to take right from the problem, is 2.10 times 10 to the 14th hertz. So remember, another way to write hertz is 1 over seconds. Okay, so I want to make sure that our units will cancel in some way. Take a minute and punch that into your calculator. And when you have finished putting that into your calculator, what should come out for most people in their calculator is something like this, 0.00000, and I'm going to round this right away. I'm going to say 143. So I do not want to leave my answer like this. This is too small of a number. It doesn't read well as a visual, and so I'm going to put this into scientific notation. This is a scientific notation number, is 1.43 times 10 to the negative 6. So now what does that mean for my units? If I notice up here, I had meters per second divided by 1 over seconds. Seconds should cancel out because this will end up in the numerator and seconds will cancel. So the unit here is meters. That also makes sense because meters was the one unit of length in my original problem. Even though I know it says I want it in nanometers, that's not what it's going to come out as from the problem. So right now this is in meters. I need to do one more step to convert this into nanometers. 1.43 times 10 to the negative 6 meters. I'm going to put meters on the bottom this time and nanometers on the top. 1 meter, there's still a billion nanometers in 1 meter. So I'm going to multiply these two numbers. And so my original number here, 1.43 times 10 to the negative 6, should get bigger, should get much, much bigger by a factor of a billion. I can go ahead and move the decimal 9 places. You might want to look at this original number to help you with that. But I should end up with 1,430 nanometers. Okay, both of those would be sufficient. Because the problem said answer in nanometers, I'll leave that circled in red. But the other one would be fine too. If it doesn't say what unit of length you're looking for, just assume it's meters. So now we want to identify the type of radiation that this is. So I'll jump ahead a little bit. I've put up a picture here of the electromagnetic spectrum in order for us to find the type of radiation that this particular wave is traveling as. So if I remember from the problem I just did, my wavelength was 1.43 times 10 to the negative 6 meters, or 1,430 nanometers. I think the meters is going to be more helpful for us on this spectrum. So notice here that wavelength is on the bottom, so that's where I'm going to look to find what type of radiation it is. I do also see nanometers right here, but that's really for the visible spectrum. And my number in nanometers, 1,430, is beyond 700. So it's not even in the visible spectrum. So this, I'm going to use this top number, 1.43 times 10 to the negative 6 meters. So I'm going to look on the bottom axis to where I find negative 6. And again, it should be past the red color of light. Or I should say not yet towards the red color of light. So that puts us in the infrared range. IR is infrared. Okay, so if it asks you for the type of radiation, you can use this electromagnetic spectrum. You can use either the wavelength or the frequency to help you determine that. I just chose to use the wavelength for this particular example. Okay, try a few examples on your own. Let me know what questions you have in class, and thanks for watching.